This is the second lecture, second part of energy balances. In this lecture, we are going to cover both mechanical energy balances and also simultaneous material and energy balances. So let's start with simultaneous material and energy balances. And the concept of this is that the energy balance must hold, and therefore you may need to perform the energy balance in order to know the material balance. So we are going to look at an example calculation to show you this. Okay, so we have a turbine discharges this steam, 200 kilograms per hour of saturated steam at 10 bar. Okay, so this steam has already had energy removed from it, and now we are going to adjust the energy of that steam by adding an additional stream of steam. And the goal of the process is to, and note we have the terminology here, it is desired. It is desired. That is written in future tense, and therefore it is the goal of the process to generate steam at 250 degrees C and 10 bar. And sure enough, if we look at our flow chart, this is the stream of steam coming out of our mixer. We are going to mix the turbine discharge with another stream of superheated steam at 300 degrees C and 10 bar. Okay, so we know that this one now is superheated. We don't necessarily know what this one is. It's also 10 bar, but it's a lower temperature. And so we don't know if that's superheated or not, but we can check by looking on the steam tables. And we're going to ask two questions here. The first question is, if no heat is added to the mixer, okay, in which case Q here would be 0, what must the values of N2 and N3 be? Okay. The second question is, let's specify the output, okay, and say we want this to be 300 kilograms per hour for N3. How much heat must be added to the mixer? Okay, so this is an example of a simultaneous material and energy balance. All right, so we know this is saturated. We have already been told this one is superheated. And we can find the H values for all of these streams on the steam tables. Okay, so this one is the saturated steam at 10 bar. And here's the enthalpy. Note that we did not need to specify the temperature, because if it's saturated at a pressure, that's enough information. Okay, can we find enthalpy for these other streams on the steam tables? Yes, we can. Okay, we know this one is superheated. All right, and we can find that H hat is 30,052 kilojoules per kilogram. Let's look for this stream here, and we find that it is also on the superheated tables, and we have the H. Okay, so now we have all of the stream variables listed. This is the mass balance. Simply 200 is equal to N2 plus N3. And the energy balance is Q dot is equal to delta H. And even though we say that it is a mixer, we have much more energy associated with the energy change than with the mixing in the process. So we will neglect the work of the mixer. And so Q dot is equal to delta H. And we can simply write H out times N dot out minus H in N dot in minus H in N dot in. So this is the sum. This one here is the sum of N dot in H hat in. Okay. And we're going to subtract the Q dot. And we can solve for that Q dot. Okay. So we have two equations and two unknowns, and we can solve this. Okay. We cannot solve the material balance without the energy balance. All right, and we can do that. Now, the two questions that I asked you were, the first one was, if no heat is added to the mixer, then what must n dot 2 and n dot 3 be? Okay, and so that's essentially solving these two equations as they are written. The second question was, let's say we need 300 kilograms per hour of stream 3, then we have to add heat. Okay, and so this is answering the second question that I had posed on the other slide. So again, the math is not complicated, but you need to identify the inlet enthalpies, the outlet enthalpies, and the givens that you have. So let's now look at mechanical energy balances, and we'll start by doing a little derivation. We're going to try to derive the Bernoulli equation, which you probably also derived or will derive in Chemie 190. Okay, so we start from our general energy balance equation, all right, and we're just going to regroup a little bit. We're going to call enthalpy U plus PV hat, which is the definition of enthalpy, right? H is defined as internal energy plus flow work, okay? And we're going to write these as velocity and change of height, okay? And that's going to equal Q dot minus W dot S. So we can, now if we substitute the density in, okay, for 1 over V, okay, we're trying to get rid of this. We're going to convert that to density. So we will put P over V, and we keep this the same and this the same. And now we're just going to divide through everything by m dot. So we have the m dot and the m dot here. Okay, so now this term here, this delta U, okay, internal energy minus a heat transfer term, okay, and so we're assuming that we're not trying to add heat, but there's always a little bit of heat in the sense of there's friction, okay, but so we're going to group these two into a thermal energy term, and it would be only due to friction because we're not going to be specifically adding heat when we have a mechanical energy balance. And we're going to leave this shaft work over here, and we may want shaft work. Okay, we may need to pump our fluid, or we may use our fluid to turn a turbine, like a waterfall or something. Okay, so this is called the Bernoulli equation. The Bernoulli equation is if there is no shaft work present, we have this equation. It reduces to this. All right, so let's do an example calculation. All right, water flows from an elevated reservoir through a conduit to a turbine at a lower level and out of the turbine through a similar conduit. We're given information here that the shaft work of the turbine is 1 megawatt. At a point 100 meters above the turbine, the pressure is 207 kilopascals. And at a point 3 meters below the turbine, the pressure is 124 kilopascals. What must the water flow rate be if the turbine output is 1 megawatt? All right, so let's look at this problem. Okay, we write the Bernoulli equation. We have a turbine, so we'll include the shaft work term. Okay, we're going to assume the friction loss is negligible, maybe because we don't know anything about it. So let's just ignore it for our back of the envelope calculation here. And so we're trying to find the water flow rate. So we are trying to solve for m dot. Okay, so note that the work is done by the system. The work is turning the water is turning the turbine. Okay, so the water is doing the work. Okay, so turbines do work. Okay, so the system is, I'm sorry, the work is done by the system. So the turbine is turning, and the work is being done. So the system is doing the work. So the work is done by the system, and we will incorporate it in as a positive value because it's being done by the system. Okay, so now let's regroup here. We're trying to solve for m dot, so I just rearranged the equation. And we have delta P, P2 minus P1. Okay, so it's negative. We have the density of water, which we can look up on the table in the back of the book, 1. All right, and then then we can calculate delta P over rho. It has this negative value. All right, we have gravity. We know the height change is also negative. And then G delta Z, okay, is going to be this, okay? And we plug those in. And since it is minus W dot S, even though the work has a positive value, we put a negative here because it is minus W dot S. All right, and so if we put all those in and we solve, we get 915 kilograms per second as our m dot. All right, so to summarize, energy is always conserved, which allows us to perform energy balances. And we can calculate our open system energy balances using enthalpies. For water, we find properties, relevant properties on the steam tables. And for a flowing liquid with no or little temperature change, we can use the mechanical energy balance equation. Okay, so now this is going to be the quiz, the video quiz 7_2.2. A fuel oil is burned with air in a furnace. The combustion produces 813 kilowatts of thermal energy, of which 65%, we don't always get all of the energy transferred, okay? In fact, that would be highly unusual. So here we have a kind of an efficiency. 65% of that heat is transferred as heat to boiler tubes that pass through the furnace. The combustion products pass from the furnace to a stack at 650 degrees Celsius. The water enters the boiler tubes as a liquid at 20 degrees C. Okay, you can find that H on the saturated steam tables. Okay, and leaves the tubes as saturated steam at 20 bar. Okay, again, you can find the H. All right, so you're going to calculate the rate at which steam is produced. So we're looking for m dot of the steam, delta H, and Q. So you can solve this, and it will be it's already posted on Canvas.